Good morning, dear children. Today we are going to start the last chapter of chemistry, chapter 4, structure of the atom. In this chapter we will learn about subatomic particles and various models that have been proposed to explain how these particles are arranged within the atom. Chapter 4, structure of the atom. It was known by 1900 that the atom was not a simple indivisible particle, but atom is divisible particles, and one of the subatomic particles atom is electron. This electron was discovered by J.J. Thomson. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiations in a gas discharge and called them canal rays. These canal rays were positively charged radiations which ultimately led to the discovery of another subatomic particle called proton. So Goldstein in 1886 discovered canal rays in a gas discharge tube experiment, and these canal rays were positively charged radiation, and the discovery of these canal rays ultimately led to the discovery of proton. Proton was discovered by Rutherford and it is represented as P+. In 1932, J. Chadwick discovered another subatomic particle called neutron. So the three subatomic particles, proton, electron and neutron. Proton was discovered by Rutherford, electron was discovered by J.J. Thomson, and neutron was discovered by J. Chadwick. Let us see the properties of proton, electron and neutron. Protons are positively charged particles and are present interior of atom. Mass of proton is 2000 times as that of the electron, and this proton is represented as P+. Electrons are negatively charged particles and are represented as E-. Mass of electron is negligible. The mass of a proton is taken as 1 unit and is charged as +1. The mass of an electron is considered to be negligible and its charge is -1. Neutrons are chargeless particles and a mass nearly equal to that of a proton. These neutrons are also present inside the atom. Clear? Thomson's model of an atom. We have learned Dalton's atomic theory in chapter 3, which suggested that the atom was indivisible. But the discovery of two subatomic particles such as electrons and protons inside the atom led to the failure of this aspect of Dalton's atomic theory. It was then considered necessary to know how electrons and protons are arranged within an atom. For explaining this, many scientists proposed various atomic models. J.J. Thomson was the first one to propose a model for the structure of an atom. Thomson proposed the model of an atom to be similar to that of a Christmas pudding. The electrons in a sphere of positive charge were like dry fruits in a spherical Christmas pudding. This Thomson's model of atom is also called watermelon model. The positive charge in the atom is spread all over like the red edible part of the watermelon, while the electrons are embedded in the positive charged sphere like the seeds in the watermelon. Let us see the features of Thomson's model of an atom. The first point is an atom consists of a positively charged sphere and the electrons are embedded in it. The second point is the negative and positive charges are equal in magnitude. So the atom as a whole is electrically neutral. So the first point is atom consists of a positively charged sphere and electrons are embedded in it. The negative and positive charges are equal in magnitude. So the atom as a whole is electrically neutral. Although Thomson's model explained that atoms are electrically neutral, the results of experiments carried out by other scientists could not be explained by this model. After the failure of J.J. Thomson's model of an atom, another scientist named Rutherford suggested a model of an atom. Rutherford designed an experiment for knowing how the electrons are arranged within an atom, and this experiment is known as Rutherford's alpha scattering experiment. In this experiment, he bombarded fast moving alpha particles with thin gold foil. Alpha particles are doubly charged helium ion and they have a mass of 4U. So the atomic number of this helium is 2 and its mass is 4. Atomic number means number of protons or electrons in helium is 2 and its mass is 4. So these alpha particles are similar to helium nuclei. It is a doubly charged helium ion. He selected a gold foil because he wanted as thin a layer as possible. This gold foil was about only 1000 atoms thick. Let us see Rutherford's alpha scattering experiment. Rutherford's experiment is known as alpha particle scattering experiment. To understand about this experiment, let us first see what alpha particles are. Alpha particles are emitted by radioactive substances. These are helium ions with double positive charge. Now let us look into the details of alpha particle scattering experiment. The setup of the experiment consisted of a thick lead box with a hole on one of its walls, a slit, a thin gold foil, and a rotating detector at the end. Inside the lead box, a radioactive substance rich in alpha particles was kept. Now let us see the experiment. Alpha particles emitted from the radioactive source pass through the hole and enter into slit to get streamlight. The thin streams of the particles then bombarded the gold foil and get scattered in different directions. The scattering pattern was shown by the detector. It was expected from Thomson's model that it should show a large number of deflections, but something else was observed actually. The detector showed that most of the fast moving alpha particles passed straight through the gold foil without any deflection. Some of the alpha particles were deflected by the foil by small angles. Surprisingly, 1 out of every 12,000 particles appeared to rebound. Such observations led to significant conclusions. Let us see what those were. As most of the particles passed straight through the gold foil, Rutherford concluded that most of the space inside the gold atom was empty. A very few particles were deflected from their path by small angles, indicating that there must be a positively charged center which was repelling alpha particles. As these particles were few in number, this led to the conclusion that the positively charged center occupies a tiny space. A few particles that are rebounded back indicate that all the positive charge of the atom was concentrated in a very small volume in the center. Rutherford named this positive center of the atom as nucleus. Looking at the properties of the particles undeflected, deflected and rebounded, and based upon some calculations, Rutherford concluded that most of the mass of an atom is concentrated in its nucleus. Based on all these conclusions, Rutherford suggested an atomic model which was known as the nuclear model of atom. According to Rutherford's nuclear model, there is a positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. It also suggested that the electrons of the atom revolve the nucleus in circular path. This model of atom is also called planetary model of atom, as the nucleus of the atom can be compared to a miniature sun, and electrons revolving around the nucleus can be compared to the planets revolving around the sun. But this model did not get much acceptance, as it said that electron keeps revolving around the nucleus. However, later it was found any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom should be highly unstable, and hence matter would not exist in the form that we know. We know that atoms are quite stable. So, nuclear model could not explain the stability of an atom, and this was its major drawback. Let us recap. Rutherford gave a nuclear model of an atom which was based on his alpha particle scattering experiment. According to the Rutherford's model of an atom, all the positive charge and mass of an atom is concentrated at the center. The center of an atom is called the nucleus. The size of the nucleus is very small as compared to the size of the atom. The electrons of an atom revolve around the nucleus in a circular path. The major drawback of this model was it could not explain the stability of the atom.